For a century, the Big Bang has been our best story about how everything began space-time matter and energy bursting into existence from an ultra-dense state. But what if that story is not the whole truth? What if the universe never truly began at all, or followed a path far stranger than a single cosmic explosion? Tonight we explore the possibilities hiding beyond the Big Bang. If you enjoy calm journeys into bold cosmic questions, please subscribe and share, and tell us in the comments what would you ask about a universe that might not have had a beginning. Thank you for watching. Now let's begin. The story of the cosmos usually begins in a very specific way. Astronomers observe that distant galaxies drift away from one another, and that the farther a galaxy is, the faster it recedes. This pattern is described as cosmic expansion. If that expansion is followed backwards in time, the usual picture says that all of space was once compressed into an extremely hot, dense state. In many retellings, this state is pushed all the way to an ideal point of zero size and infinite density, and that imagined point is called a singularity. The standard narrative then says that the Big Bang is the moment this singular state begins to expand, and that time itself starts there. In this view, the entire observable universe, with all of its galaxies, stars and planets, once occupied a region smaller than anything that can be pictured in ordinary terms. The temperature and density are described as so extreme that known forms of matter cannot exist in any familiar way. Space-time and all physical fields are said to emerge from this early phase, then cool and spread out as the universe grows. This picture is not arbitrary. It comes from the mathematics of general relativity, the theory of gravity that links the presence of matter and energy to the curvature of space-time. Shortly after this theory was introduced in the early 20th century, researchers applied its equations to a universe that is the same on large scales in every direction and at every location. Under those conditions, the solutions reveal a universe that cannot remain static. It must either expand or contract. When the expansion case is chosen, the density of matter and radiation increases without bound as the clock is turned back. In the simplest versions, all paths in space converge to the same early moment. That moment is then treated as the beginning. Over time, this mathematical result was linked to several lines of observation. Telescopes measured the pattern of galaxy recession and found that an expanding model gives a natural explanation. The detection of a faint glow of microwave radiation from every direction in the sky added powerful support. That glow, called the cosmic microwave background, looks like the cooled remnant of a much hotter earlier state. The mix of light elements observed in the universe, such as hydrogen, helium, and a small fraction of lithium, matches what would be produced if the young cosmos were once a dense nuclear furnace and then expanded and cooled. When these pieces are put together, the impression is strong. A hot early phase seems unavoidable, and the tendency is to push that phase back as far as the equations allow. At the start of this modern story, it appears natural to say that the universe began in a Big Bang, that the Big Bang was a singular event, and that nothing resembling space or time existed before it. In many popular explanations, there is a sense of closure in this picture. The question of a beginning seems answered. The narrative runs from a singular start through rapid expansion and cooling, to the slow formation of structure, and finally to the present-day universe. Yet even at this early stage in the discussion, there are quiet assumptions built into the tale. The models that lead to a singular beginning treat the universe as perfectly smooth when it's described on large scales with matter and radiation spread out evenly. They ignore the small irregularities that later grow into galaxies and clusters. They assume a simple type of matter and energy content, and they adopt a convenient way of tracking time and distance that fits the symmetries of the model. For a long period, these simplifications were reasonable. The observations that were available did not show fine detail, and the goal was to understand the broad sweep of cosmic history. The standard Big Bang model did this with impressive success, and the phrase Big Bang became almost synonymous with the idea of the beginning itself. However, as more precise measurements arrived, the universe revealed itself to be both extremely smooth and gently uneven at the same time. The smoothness on large scales remained a striking fact, but small fluctuations in temperature and density appeared in the microwave background map. Surveys of galaxies traced a delicate web of filaments and voids. The cosmos was no longer a simple ideal fluid. It was nearly uniform, but not perfectly so. This change in observational detail raises a subtle concern. If the real universe is even slightly lumpy, is it still valid to imagine that all of space can be rewound into a single point? If the matter distribution has texture, do the paths followed by light and particles in the real cosmos actually converge in the tidy way the simple model suggests? General relativity allows for many possible spacetimes, and only a few of them are perfectly smooth. In a more realistic description, there may be regions that curve differently, or paths that cannot be traced back to one shared origin. In that case, the idea of a singular beginning might be an artifact of the model, rather than a direct reflection of reality. This standard account also leaves open another question. Even if there was an early hot phase, does that phase truly represent the first instant of everything, or is it only the earliest part of the story that current observations can see clearly? The expansion that is observed today could be the continuation of a process that started in a more complex way than the simple backward extrapolation suggests. At this point, the listener is left with two layers of understanding. On one layer, the Big Bang remains the most successful description of how the observable universe has evolved from a dense hot state to its present form. On another layer, the exact nature of the supposed beginning, and even the question of whether a true beginning occurred, is less settled than the familiar story implies. Early cosmological models are built on a quiet idealization. The universe is treated as though matter and radiation are spread out smoothly at every point in space when viewed on a large enough scale. In this simplified picture, no region stands out as denser or emptier than any other, and space can be described by a single expanding grid that stretches uniformly over everything. The geometry that solves the equations of general relativity under these conditions is elegant and simple. Space either expands or contracts in the same way everywhere, and time flows in a uniform manner along each line of this expanding grid. When this ideal universe is traced back in time, the density of matter and radiation grows without limit, and the scale of space shrinks towards zero. The conclusion seems straightforward. If the model holds all the way back, then all of space and all paths through space-time converge on a common extremely early moment. That moment is tagged as the beginning of the universe. It is an image that fits easily into the mind, and it has the appeal of mathematical clarity. A smooth universe gives a smooth story, one origin, one unfolding, one vast structure, built from a single starting point. However, the real cosmos is not perfectly smooth. On the night sky, galaxies gather into clusters and long filaments. Empty regions called voids span tremendous distances. Even within a single galaxy, matter is concentrated into stars, gas clouds, and dark structures that do not shine. On smaller scales, planets form within disks of dust and gas, and in some places, like the region where Earth orbits the Sun, complex chemistry arises. None of this structure stands out in the simplest expanding model. From the viewpoint of that model, such details are treated as tiny ripples riding on top of an almost uniform sea. Observations over the past decades have made this contrast very precise. Maps of the faint microwave background radiation show that at the time this light last interacted strongly with matter, the young universe was astonishingly even. The temperature differed from place to place by only a few parts in 100,000. At the same time, those maps reveal a delicate pattern of slightly hotter and cooler regions. These variations mark locations where the density was very slightly above or below the average. Over billions of years under the influence of gravity, the denser spots draw in more matter and grow into the galaxies and clusters seen today. The universe appears to sit in a narrow regime between smoothness and lumpiness. On very large scales, it behaves almost exactly like the ideal model. On smaller scales, the details become messy and highly structured. This balance raises a subtle question about the supposed singular beginning. The singular state at the start of the simple model is not just an observation. It is the endpoint of following the smooth grid of space-time back as far as the equations will allow. If the actual universe deviates even slightly from that smoothness, then the logic that forces all paths to meet at a single point may not hold in the same way. In a lumpy cosmos, light rays and particle paths weave through a web of over-dense and under-dense regions. Some paths may intersect or focus, while others may diverge or thread around strong concentrations of matter. General relativity allows such complexity. The gravitational field is determined locally by the distribution of energy and momentum, and no rule requires all geodesics to converge in a neat way when traced backwards. The conditions that guarantee a singular beginning in the simplest models rely on assumptions about the average behavior of matter and the large-scale expansion. Once these assumptions are relaxed, the fate of geodesics becomes less obvious. The sample script that inspires this narrative points out that the early pioneers of cosmological modelling, by choosing a perfectly smooth universe, made a deliberate and useful simplification. It was an attempt to capture the broad behaviour of the cosmos without being overwhelmed by every small irregularity. That choice opened the path to the modern Big Bang picture. At the same time, it hides the very features that later give rise to galaxies and to observers who can ask about beginnings. The small deviations from perfect smoothness are not minor corrections. They are the seeds of everything structured. If the universe had been exactly uniform, no stars or planets would have formed. This observation suggests an intriguing twist. The same irregularities that make the universe interesting on large scales might also influence whether the cosmos ever truly passes through a single origin state. If there are regions where density grows especially quickly, they might form black holes or other compact objects that pinch off parts of space-time. If there are regions that expand more gently, paths through those regions might avoid certain extremes. The global behavior of all these paths together determines whether the universe as a whole possesses a sharp beginning, or whether different regions have more complicated paths that do not all meet cleanly. Another ingredient deepens the puzzle. To explain why the microwave background is as smooth as it is, cosmologists introduce a phase called cosmic inflation. In this phase, space undergoes a period of extremely rapid, nearly exponential expansion. A tiny patch that starts out smooth can be stretched until it covers a region much larger than the observable universe. This process smooths out many irregularities and pushes the cosmos toward the ideal case assumed in simple models. At the same time, quantum processes during inflation imprint small fluctuations on the stretched space, providing the seeds for later structure. Inflation, therefore, plays two roles at once. It explains the large-scale smoothness that invites the singular beginning, and it also generates the small-scale lumpiness that may complicate that beginning. In a universe with inflation, the early conditions are not simply set by initial data at a single time. They are shaped by the dynamics of the inflating field and by chance-like processes that add subtle variations from place to place. This history suggests that the concept of a single precise starting point becomes less clear. If inflation arises from a more fundamental sector of physics, its onset might not coincide with a true origin of time, but could instead mark a transition within an older space-time. In that case, the nearly smooth patch that becomes the observable universe is one region within a larger, more complicated whole. Whether that larger whole ever narrows to a singular point or whether it stretches back without a beginning is not decided by the idealized smooth model alone. The contrast between smoothness and lumpiness thus opens a first path toward doubt. The standard Big Bang story emerged from a simplified universe that is almost but not exactly the one that exists. The slight mismatch between model and reality is not yet an argument against a beginning, but it is a prompt to re-examine how firmly the singular starting point is anchored in the true structure of space-time. Cosmic inflation appears in modern cosmology as a response to a set of quiet puzzles that the simple expanding universe cannot resolve. The standard Big Bang picture explains how a dense hot state cools and thins as space grows, but when that picture is examined with more care, several features of the observed cosmos look surprisingly fine-tuned. One of the most pressing issues is the remarkable uniformity of the cosmic microwave background. Light from opposite sides of the sky has almost exactly the same temperature, differing by only tiny fractions of a degree. In a universe that has always expanded at a steady or slowly changing rate, those far separated regions could never have influenced each other in the past. There would not have been enough time for light or any signal to travel between them, yet they look as though they once shared a common state. Another puzzle lies in the overall shape of space. Measurements show that on the larger scales that can be observed, the geometry of the universe is very nearly flat. In the language of general relativity, flatness means that space is not strongly curved in a positive or negative way when large regions are averaged over. A flat universe is not the only mathematical possibility. Tiny departures from flatness would normally grow as the universe evolves, leading to a cosmos that quickly becomes either strongly curved or very short-lived. The near-perfect flatness that is seen today suggests that the early universe must have been tuned to an extreme degree, unless some process drove it toward that state. In the late 20th century, researchers proposed inflation as a way to address these and related problems. In its simplest form, inflation is a period in which the energy content of the universe is dominated by a special field whose pressure is negative and nearly constant. Under these conditions, the equations of general relativity predict that space expands in an accelerated, almost exponential fashion. Distances between points grow at an ever-increasing rate, and a very small initial region can be stretched to a size vastly larger than the part of the universe that can now be seen. Because this rapid expansion is driven by the properties of the field, rather than by ordinary matter or radiation, it smooths out many irregularities. Any initial curvature is diluted and any pre-existing clumps are spread so thin that they become negligible. A patch of space that is only modestly uniform at the beginning of inflation can become astonishingly uniform by the time inflation ends. In this way, regions that are now widely separated in the sky can share a common history. Before inflation, they were close enough to interact and to settle into a similar state. During inflation, they were pulled apart so quickly that they now lie beyond each other's horizons, yet they still carry the imprint of their shared past. The flatness problem is addressed in a similar way. As space inflates, the curvature radius grows so large compared to observable distances that any residual curvature becomes undetectable. The universe looks flat not because flatness was imposed as initial data, but because inflation pushed it into that regime. One of the most subtle consequences of inflation comes from the quantum nature of the inflating field. On very small scales, quantum fluctuations cause tiny variations in the field's energy. During inflation, these fluctuations are stretched to macroscopic sizes. When inflation ends and the field's energy is converted into ordinary particles and radiation, these stretch fluctuations become small differences in density from place to place. Over time, gravity amplifies the denser regions, drawing in more matter, and forming the seeds of galaxies and clusters. In this view, the delicate pattern of temperature variations in the cosmic microwave background is a fossil record of quantum processes that took place when the universe was extremely young. Measurements of those patterns by space-based and ground-based observatories show that they are nearly scale-invariant, meaning that fluctuations have almost the same strength over a wide range of sizes with a slight preference for larger scales. This is a hallmark of simple inflationary models and has been taken as strong circumstantial support for the inflationary idea. Inflation therefore reshapes the early part of cosmic history. Instead of a universe that simply begins hot and dense and then expands, the narrative inserts a phase in which a special form of energy drives a powerful but brief acceleration. The hot state that is usually called the Big Bang can then be reinterpreted. Rather than being the absolute beginning, it may mark the end of inflation, when the energy of the inflating field is released and converted into a dense bath of particles and radiation. In this picture, the bang is a heating event, a transition in the behavior of the universe, rather than the first instant of time itself. This change in emphasis is subtle but important. The original singular beginning enters the story through the backward extrapolation of the simple expanding solution. Inflation complicates that line of thought. Depending on how inflation starts and ends, the timeline of the universe may not have a simple single origin point. In some models, inflation itself can last for a very long time in some regions, while ending in others, leading to a patchwork of inflating and non-inflating domains. The observable universe would then be one such domain, one bubble in a larger inflating environment. In that setting, the question of what if anything happened before the hot phase inside our bubble becomes distinct from the question of whether the larger structure had a first moment. Even before such extended scenarios are explored in detail, inflation invites a revision of language. When cosmologists describe the Big Bang today, they often mean the hot early universe, whose properties can be tested through light element abundances, microwave background measurements, and galaxy surveys rather than the literal instant at which time begins. The theory of inflation shows that the hot phase may naturally grow out of a prior epoch governed by different physics. That prior epoch may itself be finite in duration, or may reach back in more complicated ways. The simple story of a universe that begins in a single explosive event gives way to a picture in which the earliest accessible moment is a transition, and the existence or non-existence of a deeper beginning becomes a subject of ongoing investigation rather than a settled fact. Once inflation is part of the picture, it becomes natural to ask how it starts, and how it ends not just in one place but throughout the whole of space-time. In the simplest descriptions, the inflating field sits in a high energy state, then slowly rolls or decays to a lower energy state. While it remains high, it drives accelerated expansion. When it drops, inflation ends, and the energy stored in the field turns into a dense mix of particles and radiation. In a basic model, this process occurs everywhere at nearly the same time, and the universe moves together from an inflating phase into the hot early state that is often called the Big Bang. However, when quantum effects are taken more seriously, this sequence does not happen uniformly. The field fluctuates randomly from place to place. In some regions it decays, and inflation ends. In other regions, fluctuations push it back up the potential, so that space there continues to inflate. The result is a patchwork cosmos. Where the field has decayed, bubbles of ordinary expanding space appear filled with matter and radiation. Around and between those bubbles, other regions remain in the inflating phase and grow at an enormous rate. This leads to what is called eternal inflation. The term does not necessarily mean that the entire universe lasts forever, but it does describe a process in which inflation once started never completely shuts off. At any moment there are zones where it has ended and zones where it still continues. the inflating zones expand so rapidly that on the larger scales their volume dominates. Within them, new bubbles keep forming. Each bubble contains its own hot early phase, its own history of cooling structure formation, and perhaps its own physical conditions. The observable universe would be one such bubble, an immense region by human standards, but a small part of the overall inflating space-time. In this framework, the Big Bang that is reconstructed from observations inside the bubble is a local event. It is the heating and onset of ordinary expansion within one pocket. The larger inflating background does not share a single synchronized beginning or ending. Different parts of it can be at different stages of evolution. Some bubbles may form earlier, others later. Some may never arise in certain directions if inflation persists there without interruption. From the standpoint of an observer inside a bubble, the past-like cone reveals a hot origin, followed by cooling and structure formation, and the simplest extrapolation points back toward a singular beginning. Yet that extrapolation only uses the physics and geometry inside the bubble. It does not directly reveal how the surrounding inflating space behaves on longer timescales. Eternal inflation therefore shifts the question of a beginning to a different level. Instead of asking whether the hot phase in one bubble had a first moment, it becomes important to ask whether the entire inflating space-time had a first moment. If the inflating field and the geometry that supports it extend without bound into the future, does that process need to emerge from a definite starting time in the past, or can it be an ongoing feature of reality that has no earlier slice? The equations that describe inflating regions can be written so that time runs arbitrarily far forward. The exponential growth ensures that new volume is constantly created and new bubbles are constantly born. Turning these equations backwards raises conceptual challenges. In some directions, following the history of a bubble back leads to the moment when inflation ended inside it, which corresponds to the hot initial state of that bubble. In other directions, tracing back could lead into the wider inflating region from which the bubble emerged. That larger region might itself have arisen from earlier stages, or it might be part of a more symmetric space-time that looks the same at all times when viewed in appropriate coordinates. The sample scientific discussion that underlies this script emphasizes that eternal inflation, despite its name, does not automatically remove the need for some kind of past boundary. There are technical arguments developed later in the story that suggest that even eternally inflating spacetimes cannot be extended indefinitely into the past under certain assumptions. But those arguments rely on average properties of expansion and on specific energy conditions. From a more intuitive viewpoint, eternal inflation already softens the idea that there is a single bang that marks the creation of everything. Instead, one sees a tree of cosmic histories branching off from an underlying process that may or may not have a root. Within each branch, the hot beginning looks like a start. Taken together, the branches form a structure in which the notion of a unique earliest event becomes less clear. The image of bubble universes embedded in an inflating background also introduces the possibility that different regions can experience different effective laws of physics. The value of certain constants, the arrangement of fields, or even the number of large spatial dimensions might vary from one bubble to another, depending on how the inflating field decays and on what deeper theory governs its behavior. In that case, the specific history inside the observable universe is one realization among many. The Big Bang in this region is then a local transition to a set of conditions that happen to allow galaxies, stars, and chemistry of the familiar kind. Whether the overarching inflating structure that gives rise to all such bubbles began at a definite time or has existed in some form without a sharp beginning is a separate question tied to the deepest properties of spacetime and the fields that fill it. In this way, inflation, when taken beyond its simplest form, quietly changes the scale of the problem. The question, did the universe begin with the Big Bang, becomes more layered. On the scale of the observable cosmos, The hot early phase remains a robust feature supported by many observations. On the larger scale of an inflating space-time with endlessly forming bubbles, that phase becomes one episode in a more extensive and more intricate cosmic process. In everyday language, a singularity sounds like a special point where something rare or extreme happens. In cosmology and in general relativity, the word has a more specific meaning and understanding. It is essential before deciding whether the universe truly began with the Big Bang. A singularity appears when the mathematical description of space-time stops working in a controlled way. In practice, this often shows up as a quantity in the equations becoming infinite, or as an inability to extend a path in space-time beyond a certain limit. At first sight, the singular state at the start of the standard expanding model is such a place. As the model is run backwards, the density of matter and radiation grows. Without bound, the scale factor that measures the size of space shrinks towards zero, and the curvature that encodes the bending of space-time becomes very large. It is tempting to say that this means the universe really did begin from an infinitely small, infinitely dense point. However, there is an important subtlety. The mathematical description of space-time is built from coordinates which are labels assigned to events. These labels are not unique. Different coordinate systems can describe the same physical situation using different numbers. A singularity in the coordinates does not always mean that space-time itself ends. Sometimes it means that the chosen labels have become inappropriate for describing a certain region. A simple example comes from describing the surface of the Earth. Lines of longitude meet at the North Pole and the South Pole. In a coordinate system that uses longitude and latitude, the longitude coordinate becomes ambiguous at the poles. That is a coordinate singularity. Nothing special happens to the physical surface there. The breakdown lies in the map, not in the territory. In general relativity, something similar can occur. Certain choices of coordinates can make the description of time or distance behave badly, even when space-time itself is smooth. Other choices can remove that apparent problem. This raises a key question. When the equations of cosmology or of gravity show a singularity, is that singularity a feature of the coordinates or a genuine edge of the physical space-time? In the case of the simple Big Bang model, the singular beginning is found in a highly symmetric coordinate system that assumes homogeneous and isotropic space. In that system, every point in space sees the same expansion. History and cosmic time is measured by the clocks of observers who move with the average flow of matter. Rewinding this coordinate grid leads all world lines to meet at a common time that plays the role of the origin. But because this construction uses strong symmetries, it is not obvious that the singularity it reveals must survive in more general descriptions. If small deviations from smoothness change the behavior of geodesics, and if different choices of coordinates can extend paths further than the symmetric system allows, then the status of the initial singularity becomes less clear. Physicists distinguish between several kinds of singular behavior. One sign that space-time may have a serious problem at a point is geodesic incompleteness, where natural paths followed by particles or light cannot be extended beyond a certain limit even in principle. Another sign is curvature blow-up, where quantities that measure the intensity of space-time curvature, built from the metric in a coordinate-independent way, become infinite. If both occur together, and if no change of coordinates can remove them, then the singularity is considered physical. It represents a place where the theory predicts that space-time comes to an end. If only the coordinates misbehave while the curvature remains finite and paths can be extended after a suitable change of variables, then the singularity is only apparent. The sample discussion that motivates this narrative uses black holes as a clear example. Their event horizons look like singular surfaces in one common coordinate system, yet that singularity disappears when a better map is used. By contrast, the central region of a simple black hole is a place where curvature invariants diverge and geodesics cannot be continued. that central point is taken as a real boundary. In cosmology, the singular beginning in the Standard Model could in principle fall into either category. In the symmetric coordinates that describe a perfectly smooth universe, the density and curvature appear to diverge as time approaches the initial moment. Whether this divergence reflects an unavoidable breakdown of space-time or only a breakdown of the simple description depends on how robust these features are when the model is generalized. If the addition of small irregularities, different forms of energy, or more complex expansion histories does not remove the divergence, then the case for a genuine beginning strengthens. If instead those refinements allow space-time to be extended smoothly beyond the surface that once looked like the start, then the picture of a true origin becomes less secure. The presence of inflation and of more elaborate early dynamics complicates the analysis further. During inflation, the universe may resemble a patch of a larger space-time, such as de Sitter space. In that wider setting, what appears as an initial boundary in the coordinates adapted to the expanding patch may correspond to a surface that can be crossed in a more global description. In that case, the singularity found in the limited coordinates would be analogous to the apparent singularity at a horizon in a black hole removable by using a broader map. These possibilities motivate a careful effort to separate coordinate artifacts from genuine physics. It is not enough to note that some quantity becomes infinite in a convenient formula. One must check whether that infinity persists when the space-time is examined using coordinate-independent measures of curvature, and whether geodesics truly end there in all reasonable extensions of the manifold. Only then can the word singularity be tied to a real limit of space-time, rather than to the limits of a specific choice of description. In the context of the Big Bang, this distinction matters because it controls how strongly one can say that time itself began. If the initial state of extreme density is a true curvature singularity beyond which no extension is possible, then the hot early universe does mark a genuine boundary. If, on the other hand, the apparent singularity can be interpreted as the edge of a chart that covers only part of a larger spacetime, then the Big Bang might resemble a horizon, rather than an absolute starting point. In that case, asking what lies beyond it becomes meaningful, even if the current theory does not yet provide a clear answer. In the study of gravity, black holes provide a concrete place where the difference between a coordinate singularity and a physical singularity becomes clear. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it passes a certain boundary. That boundary is called the event horizon. Outside the horizon, light rays and particles can still travel outward if they move in the right direction. Once they are inside, all possible paths lead inward toward the center. To describe this situation mathematically, physicists often start with the metric found by Carl Schwarzschild. In Schwarzschild, coordinate spacetime outside a simple, non-rotating black hole is described by a radial coordinate and angular part that describes directions on a sphere, and a time coordinate that measures the ticking of distant clocks. In these coordinates, the line element looks well behaved, far from the black hole, but becomes strange at the event horizon. Certain coefficients in the equations blow up or vanish there, and the time coordinate appears to freeze as an object falls toward the horizon. To a distant observer who uses these coordinates in falling matter, seems to slow down and never quite cross the horizon. The mathematics suggest that something singular might be happening at that surface. However, an observer who falls freely toward the black hole does not experience anything special when crossing the event horizon of a large one. The tidal forces which measure how much gravity stretches and squeezes can be small at the horizon if the black hole is massive enough. The local physics there can be ordinary. The freely falling observer continues inward without feeling a sharp boundary. This mismatch between the apparent singular behavior in the Schwarzschild description and the smooth passage experienced in free fall hints that the problem lies in the choice of coordinates. To test this idea, physicists construct alternative coordinate systems that cover the same spacetime. One example is given by Eddington-Finkelstein coordinates, in which the time coordinate is mixed with the radial coordinate in a way that follows the paths of light rays more naturally. In these coordinates, the metric remains regular at the event horizon. Light rays that skim along the horizon and rays that cross it can be followed smoothly, and there is no sudden breakdown of the description. Another useful set of coordinates called Kruskal-Shekheres coordinates goes further and reveals the full analytic extension of the simplest black hole solution. In that extended picture, the event horizon appears as a harmless null surface, a light-like boundary that can be crossed by particles and light without encountering infinite curvature. The central region at zero radius, on the other hand, remains a place where curvature invariants diverge and where geodesics come to an end. No coordinate change can remove that central singularity. It is a genuine feature of the spacetime predicted by the classical equations. The distinction is now sharp. The event horizon is a coordinate singularity in the Schwarzschild chart because the bad behavior disappears when better coordinates are used. The central point is a physical singularity because no change of chart makes the region regular, and because natural paths cannot be extended beyond it. This lesson is illustrated in a compact way using Penrose diagrams. A Penrose diagram compresses infinite distances and times into a finite drawing while preserving the causal structure, meaning the patterns of which events can influence which others by signals that move at or below the speed of light. In these diagrams, light rays always travel along lines tilted at 45 degrees, so it is easy to see which events can send light to which others. The event horizon is drawn as a slanting line from which light can move inward, but never outward, while the central singularity appears as a final boundary beyond which no world line continues. Outside the horizon, world lines can either fall inward or remain outside forever. The diagram also reveals additional regions that are not visible in the original Schwarzschild coordinates. There can be a region that behaves like a white hole, where matter and light can emerge but cannot enter, and regions that resemble a second exterior universe. Whether these extra regions are realized in nature is uncertain, because real black holes form from collapsing stars and are influenced by quantum effects that the simple solution does not include. What matters for the present discussion is that the mathematics permits the spacetime to be extended smoothly beyond what once looked like a limiting surface. The event horizon is not the end of spacetime. It is the edge of a map that covers only part of the full geometry. An observer who bases intuition solely on Schwarzschild coordinates might think that the horizon is a place where time stops and that nothing ever truly crosses. A more complete description shows that this impression is a coordinate artifact. Infalling matter does cross, and in its own frame of reference it does so in a finite amount of proper time. After crossing all allowed trajectories, carry it deeper inward until it encounters the true singularity at the centre. This example offers a cautious guide for cosmology. When a singularity appears in the equations that describe the universe, it is necessary to ask whether that singularity marks a genuine edge of space-time or only the limit of a particular choice of coordinates and symmetries. Black holes demonstrate that a surface which once looked like the beginning or end of time in one chart can turn out to be a regular part of a larger space-time in another. At the same time, they also show that some singularities resist all such attempts at extension and remain as candidates for real boundaries where the classical description fails entirely. For the freely falling traveller, the interval between passing a distant marker and crossing the horizon is measured by an ordinary wristwatch and has a perfectly finite duration. The strange picture of frozen motion arises only because the distant coordinates stretch the description of time near the horizon. By keeping both viewpoints in mind, one anchored far away and one carried inward with the motion, it becomes easier to separate features that belong to the coordinate grid from those that belong to the underlying spacetime itself. In general, relativity motion in a gravitational field does not need an external force. A small body that is not pushed or driven by anything else simply follows the natural shape of spacetime. Its world line, the trace of its history through time and space, is called a geodesic. In an ordinary flat space with no gravity, the straightest possible path between two events is a straight line. In curved space-time, geodesics play the role of straight lines in a more general sense. They are the paths that extremise the interval between events according to the geometry given by the metric. Massive particles follow time-like geodesics. Light follows null geodesics, which are paths along which no time passes for an idealized photon. These curves capture the way gravity guides motion without invoking a traditional force. Once a geodesic is chosen by initial position and velocity, it is fixed by the geometry. A spacetime is said to be geodesically complete if every such path can be extended arbitrarily far into the future and into the past. That means that along each geodesic, the parameter that measures distance or time never reaches a final finite value at which the curve suddenly ends. In a complete spacetime, an ideal particle or light ray can, in principle, continue its journey without ever encountering an internal boundary imposed by the geometry itself. There may still be edges if matter is cut off, or if one restricts attention to a limited region, but the mathematical spacetime can be extended beyond any finite endpoint of the path. Incompleteness is the opposite situation. A spacetime is geodesically incomplete if there exist geodesics that cannot be extended beyond some finite value of their parameter. For an object travelling along such a curve, the journey simply stops after a finite amount of proper time or a fine parameter, not because the object decays or collides with something, but because the space-time in which it moves ceases to be defined. This type of incompleteness is taken as a rigorous signal that space-time contains a boundary. It is more precise than noting that some coordinate quantity becomes infinite because it does not depend on how the coordinates are chosen. Geodesic incompleteness plays a central role in singularity theorems. These theorems, developed in the late 20th century, show that under fairly general conditions, certain physical situations force the existence of incomplete geodesics. For example, if matter satisfies reasonable energy conditions, and if there is enough gravitational focusing, then collapsing regions that form black holes must contain time-like or null geodesics that cannot be continued into the future. In an expanding cosmological setting, similar reasoning can be used to argue that geodesics cannot be extended infinitely far into the past. The details of these theorems involve technical assumptions about energy densities, causal structure, and the presence of trapped surfaces, but the conceptual thread is simple. Gravity through the curvature of space-time can focus families of geodesics. When geodesics converge strongly, they can form caustics where the description breaks down. Under sustained focusing, this breakdown becomes a genuine incompleteness rather than a removable coordinate issue. To see how this relates to the Big Bang, imagine the collection of all geodesics that represent the histories of galaxies, stars, and light rays in a simplified model of an expanding, nearly homogeneous universe. Each galaxy roughly follows a time-like geodesic that moves with the average flow of matter. Light emitted from one region and later detected in another traces a null geodesic between those events. If the expansion has been going on for only a finite amount of cosmic time, then running these paths backward leads to a point at which something special must happen. In the standard smooth model, all geodesics meet the initial singular surface after a finite interval. They cannot be extended beyond it, and so the space-time is geodesically incomplete to the past. One might then interpret the Big Bang as the place where all these world lines begin. However, once the universe is described more realistically with small fluctuations in density, and with more complex behaviors such as inflation, the pattern of geodesics becomes more intricate. Light rays weave through regions of slightly different curvature. The histories of matter particles are deflected by inhomogeneities, by the formation of structures and by local gravitational fields. Some geodesics may fall into black holes and end in central singularities. Others may avoid such fates and travel through more gently curved regions. Whether all geodesics still terminate at a common boundary in the past, or whether some can be extended further back in some wider space-time is then a subtle question. It is not enough to look at the behavior of a single coordinate chart. One has to examine the global structure and ask whether any extension exists in which the paths continue. An important point is that geodesic incompleteness does not by itself guarantee that space-time curvature becomes infinite. There can be models in which geodesics end even though the curvature scalars remain finite along them. In such cases, the incompleteness still signals a boundary, but the nature of that boundary may be less violent than the picture of a point of infinite density suggests. Conversely, extremely high curvature does not automatically imply incompleteness if the space-time can be extended in a mathematically consistent way through the high curvature region. In practice, when both geodesic incompleteness and curvature blow-up occur, together in a coordinate-independent manner, the case for a true physical singularity becomes strong. In the cosmological context, the question is whether the observed expansion, combined with reasonable assumptions about matter and energy, forces all geodesics to share a finite path length, or whether there exist consistent models in which at least some geodesics extend indefinitely into the past. If every attempt to construct such an extension fails, then the Big Bang retains its status as a genuine boundary. If, on the other hand, there are ways to embed the observed region of the universe into a larger space-time where certain geodesics can always be prolonged, then the beginning becomes less absolute. Under that view, the hot early phase may mark a transition inside a more extensive structure, rather than the origin of all geodesics. The challenge is to decide using the tools of general relativity and the hints from observation which of these possibilities is realized in the actual cosmos. In the late 20th and early 21st centuries, cosmologists turned the vague question of a beginning into something that could be tested within the language of general relativity. Instead of asking in general terms whether the universe had a first moment, they asked whether the space-time that describes an expanding cosmos can be geodesically complete to the past. Earlier singularity theorems developed by Roger Penrose and Stephen Hawking and others already gave strong hints that a universe like ours cannot be extended indefinitely into the past under reasonable physical assumptions. Those theorems relied on conditions about the energy content of matter, such as the idea that energy density measured by any observer is never negative. They also made use of global properties that encourage the focusing of geodesics. Together, these ingredients produce conclusions that either collapsing regions must contain singularities, or that expanding cosmologies must have some form of past boundary. However, it remained possible to wonder whether the assumptions used in those proofs might fail near the earliest times, or whether inflationary scenarios offer a route around a beginning. A more recent line of work sharpened this issue in a way that is both simple to state and challenging to escape. 3 researchers, Arvind Borde, Alan Guth, and Alexander Vilenkin, examined a broad class of spacetimes in which the universe expands on average along at least one family of geodesics. Their central condition does not require detailed knowledge of the matter content or of specific energy inequalities. It only assumes that if an observer traces a path backward in time along a world line that samples the general expansion, the average rate of expansion encountered along that path is positive. In such a picture, the trio showed that the geodesic in question cannot be extended arbitrarily far into the past. Measured in its own natural time parameter, it reaches a finite limit beyond which there is no more space-time. In other words, any universe that has on average been expanding throughout its history is geodesically incomplete to the past. This conclusion has an important consequence for inflationary cosmology. Inflation describes a phase in which the expansion rate is very high and nearly constant. Models of eternal inflation suggest that some regions inflate forever into the future, while bubbles like the observable universe peel off and stop inflating. At first glance, this might suggest a universe that simply has no beginning a process that continues without end in both directions of time. The theorem by Bordeguth and Vilenkin shows that this hope is hard to sustain if the expansion along typical geodesics has always been positive. Even an eternally inflating universe dominated by rapid growth cannot be extended indefinitely into the past under that average expansion condition. Somewhere along each such geodesic there must be a boundary. The geodesic is incomplete. It is important to be precise about what this boundary means and what it does not mean. The theorem does not say that the boundary is a singular point of infinite curvature. It does not claim that all of space-time collapses to a single origin with well-defined coordinates. It simply states that within the framework of classical general relativity and the assumption of positive average expansion, at least some geodesics reach the end of their past after a finite interval. Beyond that, the theory as it is currently written has nothing more to say. That absence of an extension can be interpreted as a beginning in a broad sense. There is no way within the given space-time to follow the history of those geodesics further back. Whether the boundary is a soft edge where classical ideas fail and some quantum description takes over, or a hard singularity where curvature diverges is not specified by the theorem itself. The strength of this result lies in its generality. It does not depend on the universe being exactly smooth or exactly described by a specific simple metric. It does not rely on a particular pattern of matter or on detailed assumptions about energy conditions that might be violated in exotic circumstances. Instead, it ties the existence of a past boundary to the broad fact of persistent expansion. If space has on average been stretching along a given path, then that path cannot have an infinite classical past. There is a sense in which expansion uses up the room available in the backward direction. Still, there are possible ways in which the universe could avoid the conclusion, and these options point directly towards scenarios in which the cosmos does not truly begin with a single Big Bang event. One class of models posits that the expansion seen now was preceded by a phase of contraction. In such a picture, the universe first shrinks, then reaches a minimum size, and then begins to grow again. Along a geodesic that passes through this bounce, the average expansion rate over a long interval might be 0 or even negative because the period of contraction offsets the later growth. The key assumption of the theorem is then violated, and the proof of past incompleteness does not apply. Another possibility is a universe that spends an extended time in a nearly static or very slowly evolving state before entering the expanding era. In that case, the average expansion measured over the entire past might not be strictly positive. Once again, the theorem does not rule out such histories. However, these escape routes come with their own complications. Many bouncing or emergent models require forms of matter or effective physics that violate the usual energy conditions in general relativity or invoke new ingredients such as quantum gravity effects at high densities. That is not a proof that they are impossible, but it does mean that they operate outside the regime where the classical theorems were designed to apply. In a way, this is the point. To avoid a beginning within the classical framework, the universe seems to need new physics. Either the average expansion condition must be broken, or the relation between energy and curvature must be altered, or the entire description of space-time must be replaced by a quantum structure in which the notion of a geodesic itself is modified. From the observational side, the theorem does not directly tell astronomers what they will see on the sky. Instead, it provides a conceptual boundary condition on the space of allowed cosmological histories. Any model that describes the universe as always expanding in some suitable average sense, from the earliest times all the way to the present, must accept that some form of past incompleteness is built in. That incompleteness might take the form of a big bang like singularity, or a phase where classical spacetime ceases to be a good description, or an interface with a more fundamental regime. What it cannot be under the assumptions of the theorem is an infinite classical past in which the same expansion simply continues without origin. The theorem by Bordguth and Vilenkin therefore sits at a delicate point in the story. It does not fully close the door on a universe without a true beginning, because models that violate its key assumption remain logically open. Yet it makes clear that a smooth, ever-expanding cosmos governed everywhere by ordinary general relativity cannot stretch back forever. Somewhere behind the hot early phase and even behind any extended inflationary arena, there must be a boundary beyond which the classical picture does not reach. Whether that boundary is interpreted as the first moment of time or as the surface where a deeper description waits remains an open question for both theory and observation. The idea of geodesic incompleteness gives one way to diagnose a boundary in space-time, but it leaves open the question of how severe that boundary really is. To sharpen the picture, cosmologists also examine curvature. In general relativity, curvature is not a vague notion. It is encoded in precise quantities that can be built from the metric in a way that does not depend on coordinates. These curvature scalars measure how strongly space-time is bent by matter and energy. In familiar regions such as the surroundings of a star like the Sun or the low-density spaces between galaxies, these measures have finite values. Near a classical black hole singularity at the centre, they grow without bound. When a curvature scalar becomes infinite along a path that reaches a boundary in finite time, and when no choice of coordinates can tame that growth, this is taken as a strong sign that the singularity is physical. Space-time itself ends there, at least according to the classical theory. If, on the other hand, geodesics end, but curvature remains finite and smooth, the situation is more ambiguous. The incompleteness still marks a boundary, but the boundary might be extendable in a different description, just as the event horizon of a black hole becomes regular when a better coordinate chart is used. This distinction becomes important when the focus turns back to the early universe. In simple expanding models that lead to a Big Bang singularity curvature, scalars blow up as the scale factor goes to zero. Density and temperature rise without limit, and the mathematical quantities that track space-time bending diverge. The singularity is then both geodesically incomplete and curvature singular. It is a natural candidate for a true beginning. But as soon as more complex histories are considered, the relationship between incompleteness and curvature becomes less direct. Researchers have explored cosmological models in which the universe does not always expand. In some, there is an earlier phase of contraction followed by a bounce into expansion. In others, there may be an extended static or slowly changing phase before the onset of faster growth. A more recent study examined such possibilities by applying a curvature test to a range of expansion histories. Instead of asking only whether geodesics end it, asked whether curvature inexorably diverges near the putative pass boundary in each case. The results show a pattern. For universes that expand throughout their entire history, with no prior contraction or static era, the tendency toward a curvature singularity at the pass boundary is strong. In those cases, as the clock is turned back along curves that follow the average expansion curvature typically increases and becomes unbounded, matching the picture of a classical Big Bang. In contrast, for models in which the universe first contracts, then bounces and expands, or in which it emerges from a prior static phase, there are scenarios where curvature does not blow up in the same way. geodesics can still be incomplete in the sense that they reach a limit in finite time, but the curvature scalars remain finite as that limit is approached. In those cases, the supposed beginning looks less like a point of infinite density, and more like a surface where the classical description is incomplete but not violently singular. However, these gentler beginnings do not come for free. The same analysis finds that many of the expansion histories that avoid curvature singularities at the past boundary also violate standard energy conditions. These conditions express the idea that energy density as measured by any observer should not be negative, and that matter behaves in ways that are broadly compatible with familiar physics. When a cosmological model requires sustained violations of such conditions, it suggests that new physics is in play, that new physics might be a form of exotic matter or effective behavior arising from quantum gravity at high densities, or some modification of the relation between energy and curvature. Whatever its origin, it means that the universe avoids a Big Bang only by stepping outside the conservative domain, where general relativity with ordinary forms of matter is expected to apply. The study also highlights one special case that touches directly on inflation. An inflating universe with pure exponential expansion can be described as a patch of a larger spacetime known as de Sitter space. In this idealized case, the scale factor shrinks steadily when traced into the past but never quite reaches zero. The boundary that appears in the coordinates adapted to the expanding patch resembles the past edge of a Penrose diagram. According to the theorem by Bordguth and Vilenkin, such a spacetime is still geodesically incomplete to the past along certain paths. Yet as the curvature test shows, there exists a way to embed the patch into a larger de Sitter geometry, in which curvature remains finite and certain null geodesics can be continued beyond the apparent boundary. In that view, the past edge of the inflating region looks more like a coordinate singularity than a hard curvature singularity. It marks the edge of one chart, not necessarily the end of spacetime itself. This extension is delicate. To make it work, the patch of inflating universe must join smoothly onto the larger de Sitter space. That smoothness requires that the energy driving the exponential expansion dominates over any density fluctuations near the boundary. If fluctuations grow too large, they disturb the geometry and can close off the extension, turning the would-be gentle boundary back into a hard singularity. Here the lumpy nature of the real universe reappears. The same small inhomogeneities that seed galaxies, stars and planets also make it harder to maintain a perfectly smooth transition into a larger space-time. If they are significant near the earliest times, they can enforce a curvature singularity, where an idealized smooth model would have allowed an extension. In this way, the very irregularities that are essential for structure might also reinforce the presence of a true beginning. From a broader perspective, the curvature tests show that geodesic incompleteness and curvature blow-up do not always coincide. There are cosmological histories in which space-time viewed through the lens of classical general relativity has a past boundary, but does not necessarily crush all matter and geometry into an infinitely sharp point. Such boundaries may hint at a phase where space-time as a smooth manifold gives way to another kind of description, perhaps quantum or discrete. At the same time, for the class of universes that resemble the one seen today with sustained expansion and real inhomogeneities, the tendency toward a genuine singular Big Bang remains strong. The curvature often does grow without limit as the boundary is approached, unless the physics of the early universe departs significantly from the familiar rules. The interplay between geodesic incompleteness and curvature behavior therefore refines the question of the beginning. It suggests that there are many ways for a universe to have a past boundary, and that not all of them involve an infinitely dense origin. It also makes clear that avoiding a sharp Big Bang in a universe like ours is not straightforward. Either the expansion history must include phases that alter the average behavior such as contraction, or long static epochs, or the energy content and gravitational laws must be modified so that classical expectations about curvature no longer hold. In each case, the idea of a universe that did not start with a single explosive Big Bang shifts from a simple denial of a singularity to a more complex claim about new regimes of physics beyond the reach of current observations. In thinking about a universe that does not truly begin with a Big Bang, one of the most direct ideas is to let the cosmos have a history before the hot phase. Instead of starting from a singular point, the universe might first contract to reach a minimum size and then bounce into expansion. Another possibility is that it spends an extremely long time in a nearly static or slowly evolving state before entering the more rapid growth that is seen today. These scenarios change the average behavior of expansion in a way that evades some of the arguments for a sharp beginning. They also reveal how strongly the standard picture is tied to the assumptions built into classical general relativity. In a bouncing model, the scale factor that measures the size of the universe decreases during a contracting era. Distances between galaxies shrink and densities rise. At some stage, instead of continuing toward a singularity, the contraction halts and reverses. The scale factor reaches a non-zero minimum and then grows again. Geodesics that follow the average motion of matter can then be extended through the bounce. From the viewpoint of such a curve, there is a past beyond the hot dense state that resembles the start of the observable expansion. That past lies on the contracting side. The Big Bang becomes a transitional episode rather than an ultimate origin. To make such a bounce work, the physics that governs gravity and matter must behave differently from the familiar case. Under ordinary conditions, gravity tends to enhance contraction, not reverse it. As matter collapses, its density and pressure grow, and the attractive effect of gravity strengthens. In the classical theory, with simple forms of matter that obey standard energy conditions, a contracting universe that reaches high densities is driven toward a singular state rather than being gently turned around. Avoiding that fate requires a new ingredient. Some models introduce a special field whose pressure becomes strongly negative at high densities, creating a repulsive effect that halts the collapse. Others invoke corrections to the gravitational equations that become important near the bounce, perhaps motivated by ideas from quantum gravity such as loop, inspired modifications that prevent certain geometric quantities from shrinking below a minimum. Each of these proposals has different implications. In some versions, the pre-bounce universe resembles the post-bounce one with similar laws and similar large-scale properties. In others, the contracting phase may be very different, perhaps dominated by stiff forms of matter that smooth out anisotropies and irregularities. There are scenarios in which cycles repeat with the universe going through many rounds of contraction and expansion, and scenarios in which only a single bounce occurs. What they share is the attempt to replace the singular beginning with a high-density transition in which the equations do not produce infinite curvature. Nearly static or emergent models pursue another route. In these pictures, the universe spends an enormous time in a quasi-steady state. The scale factor changes very slowly and the geometry remains almost fixed. Tiny processes take place, but on the larger scales there is little overall evolution. After this long plateau, some mechanism triggers a departure from the static regime. The universe then enters an inflationary or rapidly expanding phase that eventually leads to the hot conditions associated with the Big Bang. From the perspective of such a model, the hot phase is again a relatively recent development set within a much longer story. The average expansion over the entire history can be close to zero if the static era dominates, which allows the model to escape certain theorems that apply only when expansion has always been positive on average. These alternatives show concretely how a universe can avoid the narrow condition that everything has always been expanding. Yet they do so at a cost. Many bouncing and emergent scenarios require departures from the usual energy conditions. They may need matter with unusual pressure, effective negative energy densities or modifications of gravity that are not yet derived from a complete underlying theory. They must also contend with observational constraints. The structure seen in the cosmic microwave background and in the distribution of galaxies encodes details of the early universe. Any model that replaces a simple Big Bang with a bounce or an emergent phase has to reproduce those patterns with high accuracy. It must explain why the universe is nearly flat, why the fluctuations in the microwave background have the spectrum they do, and why no obvious relics of a prior contraction or static epoch are seen. Some proposals address these challenges by combining a bounce or emergent phase with inflation. In such hybrids, the universe first exists in a contracting or nearly static state, then undergoes a bounce or transition, and soon after enters an inflationary phase that smooths and stretches space. Inflation then helps erase many traces of the earlier history, leaving behind a cosmos that, from the viewpoint of current observations, looks very similar to one that simply began in a hot Big Bang. In this way, the observable universe could have a prehistory without leaving clear imprints that are easy to detect. The question then shifts from what happened to what can even in principle be inferred from present data. At the same time, there is a conceptual tension. If the physics needed to cause a bounce or maintain a long static state originates in quantum gravity, then strictly speaking, the classical picture of a smooth space-time evolving through that phase may be misleading. The very notion of a continuous geodesic might break down when the fabric of space-time is no longer well described by a differentiable manifold. In that case, talking about extending geodesics through the bounce or across an emergent era becomes an approximation useful for intuition but not fundamental. The deeper theory might involve discrete structures or radically different variables in which the question of a beginning takes a new form. Despite these complications, bouncing and emergent scenarios serve an important role in the exploration of cosmic origins. They illustrate that the link between an expanding universe and a singular Big Bang is not unbreakable. By changing the early behavior of expansion, or by altering the relation between energy and curvature, one can construct worlds in which the hot phase is not the first page of the story. At the same time, the difficulty of building such models in a way that respects both fundamental physics and the wealth of precision data highlights how restrictive the actual universe is. Any alternative to a singular beginning must fit within tight observational and theoretical bounds, and it often ends up looking at accessible times very similar to the standard Big Bang scenario it tries to extend or replace. In many cosmological models, the observable universe is described by a family of solutions known as Friedmann, Lamette, Robertson-Walker spacetimes. In these models, space is homogeneous and isotropic on large scales, meaning that every direction and every location look similar when averaged over vast distances. The geometry is characterized by a scale factor that tells how distances between co-moving points change with time, and by a parameter that sets whether space is flat, positively curved, or negatively curved. When matter and radiation are the main components, the scale factor evolves according to simple equations that link its rate of change to the density of energy in the universe. When a cosmological constant or an effective dark energy component is present, another behavior emerges. The expansion tends to accelerate, and at late times the scale factor grows in an approximately exponential way. A spacetime in which a positive cosmological constant dominates, and other forms of matter are negligible approaches a very specific geometry called de Sitter space. De Sitter space is the maximally symmetric solution of the vacuum Einstein equations with a positive cosmological constant. It has constant positive curvature and can be visualized in higher dimensional embeddings as a hyperboloid surface in a flat space of one higher dimension. Different coordinate systems can be laid over de Sitter space, each covering part or all of it, and each making different features of the geometry explicit. One such coordinate choice resembles an expanding flat universe. In these so-called flat slicing coordinates, space at each instant looks like an infinite flat three-dimensional space that stretches uniformly as time moves forward. The metric in this slicing has the same form as a flat Friedmann-Lemaitre-Robertson-Walker model with an exponentially growing scale factor. For an observer who uses these coordinates, de Sitter space appears as a steadily inflating universe. However, the flat slicing does not cover the entire de Sitter manifold. It only describes a patch bounded by past and future horizons. Light rays that begin outside this patch never enter it, and light rays that leave it cannot return. From the viewpoint of the observer, co-moving with the flat slicing, there is an apparent past boundary beyond which the coordinates do not extend. In a Penrose diagram of de Sitter space, this patch occupies a diamond-shaped region. Its lower edge behaves like a past horizon. In coordinates adapted to the flat slicing, that lower edge looks like a limit as time goes to negative infinity, while the scale factor shrinks towards zero, but the full diagram shows that the manifold continues beyond it. There are other regions of de Sitter space that are not described by the flat slicing, but are perfectly regular in the global geometry. This picture becomes relevant for the early universe, when one notes that a flat inflating Friedmann-Lemaitre-Robertson-Walker model can be treated mathematically as a patch of de Sitter space in almost the same way. If the expansion is driven by an energy component that behaves like a cosmological constant, the local geometry near a co-moving observer is very close to that of de Sitter space in flat slicing. In that case, the region that evolves into the observable universe can be mapped onto one of the diamond-shaped patches on the de Sitter diagram. The hot Big Bang phase that follows the end of inflation then sits inside this patch after the inflating era has converted its energy into matter and radiation. To an observer who reconstructs cosmic history using only the flat Friedmann-Lemaitre-Robertson-Walker coordinates, there may appear to be a past boundary where geodesics end and where the scale factor extrapolates to zero size. The work inspired by the curvature tests and by the extension properties of de Sitter space asks whether this past boundary is truly the end of space-time, or whether it is more like the event horizon of a black hole in Schwarzschild coordinates. In de Sitter space itself, null geodesics that seem to approach the past edge of the flat patch can in fact be traced through that edge when one switches to global coordinates that cover the entire manifold. The region outside the patch is not singular. Curvature scalars remain finite everywhere. If the inflating patch of cosmic history is genuinely part of a larger de Sitter-like spacetime, then some of the apparent geodesic incompleteness seen in the restricted coordinates might be removed in a more complete chart. The Big Bang boundary would then be a coordinate boundary rather than an unavoidable rupture. For this extension to make sense in a cosmological setting, the matching between the Friedmann-Lemaitre-Robertson-Walker region and the surrounding de Sitter space must be smooth. The metric and its first derivatives, which control distances and curvature, have to fit together without jumps or tears along the interface. This smoothness is easiest to achieve when the energy density responsible for inflation or late time acceleration dominates over any irregularities. In effect, the space-time must be close to perfectly de Sitter, near the would-be past boundary. Under those conditions, one can imagine continuing null geodesics that skirt the edge of the observable patch into a wider region, just as one extends light rays across the event horizon in Eddington-Finkelstein coordinates. In the real universe, though, there are small but definite deviations from perfect smoothness. Even during inflation, quantum fluctuations in the inflating field generate tiny variations in energy density. that later seed the structures seen in the microwave background and in the galaxy distribution. At extremely early times, if those fluctuations reach significant strength, near the would-be matching surface they disturb the curvature enough to spoil the simple de Sitter extension. Instead of a gentle horizon-like boundary, the past edge can become a place where curvature grows rapidly and where the de Sitter embedding fails. In that case, null geodesics that seemed ready to pass into the wider space-time instead terminate, and the opportunity to view the Big Bang as a coordinate singularity is lost. The delicate nature of this matching underscores how finely the question of a beginning can depend on details of the early universe. In an idealized model with exact symmetry and a pure cosmological constant, the inflating region slides comfortably into a larger de Sitter space. The pass boundary of the patch is then not a true origin. It is a line drawn by a choice of coordinates that cover only part of the manifold. In a more realistic model where the same inflationary process that smooths the cosmos also imprints inhomogeneities, the pass boundary is less forgiving. The small ripples that are essential for forming galaxies can, when traced far enough back, contribute to closing off the extension and restoring a hard boundary in the past. From the standpoint of speculative cosmology, embedding the observable universe into a larger de Sitter structure offers a concrete way to picture a cosmos that does not begin with the Big Bang. The hot phase and even the inflationary era become features of one region inside an older spacetime. Other regions, perhaps beyond any possible observation, might have their own histories. Whether that broader de Sitter space is itself eternal to the past, or arises from an even deeper process, is another layer of the puzzle. The key point is that in this view, the Big Bang is not the birth of the manifold, but the interior of a patch, analogous to a coordinate wedge cut out of a larger geometry. At the same time, the need for near-perfect smoothness at early times, and the evidence that the real universe contains fluctuations from very early on, show that this embedding is not guaranteed. It is a logical possibility rather than a confirmed feature. The observable universe may be a region of a larger de Sitter, like space-time, or it may be a domain that genuinely comes to an end when traced back along all meaningful geodesics. In the absence of direct access to the putative, larger manifold cosmologists must rely on subtle signatures in the sky and on the internal consistency of their theories to judge which picture is more plausible. The structure of the universe rests on tiny departures from perfect uniformity. In the language of cosmology, these are density fluctuations, small differences in how much matter and radiation fill different regions of space. Observations show that at the time when the cosmic microwave background is released, the relative size of these differences is only of order 1 part in 100,000. The temperature of the background varies by about this fraction from place to place, and these temperature patterns trace underlying variations in density. That smallness is striking. A universe with no fluctuations at all would remain smooth and almost featureless. A universe with much larger fluctuations at early times would fragment quickly into compact clumps and empty voids. The real cosmos sits between these extremes. It is smooth enough on large scales for the Friedmann-Lemaitre-Robertson-Walker description to work very well, yet lumpy enough on smaller scales to form galaxies, stars and planets. These ripples arise naturally in many inflationary models. Quantum fluctuations in the field that drives inflation produce random variations in energy density on very small scales. As inflation stretches space, those variations are carried to larger scales and become classical perturbations in the curvature of space-time. When inflation ends and the energy of the inflating field is converted into hot matter and radiation, the perturbations appear as slight over and under densities in the primordial plasma. Gravity then acts slowly on this pattern. Regions that start slightly denser pull in more matter, while regions that start slightly emptier lose matter to their surroundings. Over billions of years, the initial ripples grow into the web of structure that galaxy surveys now reveal. From one viewpoint, these fluctuations are a gentle feature. They can be described mathematically as small corrections to the background expansion. Cosmologists use linear perturbation theory to study how they evolve. In that approximation, the background Friedmann, Lemaitre, Robertson, Walker universe continues to expand smoothly, while the fluctuations ride on top of it, at first remaining small and then gradually growing. This separation between the smooth background and the ripples allows precise predictions. The detailed shape of the power spectrum of fluctuations, which encodes how strong they are at different length scales, can be compared to measurements of the microwave background and of galaxy clustering. The close match between prediction and observation is one of the successes of modern cosmology. From another viewpoint, the fluctuations are a disruptive ingredient. They represent real departures from homogeneity. In regions that become strongly overdense, the local expansion can slow, stop, or reverse, and collapse can lead to compact structures and eventually to black holes. In regions that are underdense, matter drains away and expansion accelerates. When geodesics are traced backward through such an inhomogeneous landscape, they do not all converge in the orderly way seen in a purely smooth model. Some pass through regions that will later form black holes. Others run through relatively empty corridors. The global structure of space-time becomes more complicated, and the fate of geodesics in the deep past is less obvious. In the discussion of possible extensions beyond the apparent Big Bang, these small irregularities play a double role. On the one hand, if the universe were exactly smooth, it would be easier to embed the inflating region into a larger de Sitter like space, and to view the past boundary of the observable patch as a coordinate horizon. In such a perfectly symmetric case, curvature remains finite everywhere, and null geodesics can often be continued across the boundary in a suitable global chart. On the other hand, in a more realistic universe, with genuine fluctuations, the matching between the local patch and any putative larger manifold becomes more delicate. Where overdensities grow, curvature can increase more rapidly than in the smooth background. Even if the average behavior is benign, specific directions in space-time may encounter regions where focusing of geodesics is strong. The curvature tests developed in recent work highlight this tension. They show that in some idealized expansion, histories, notably those with exact de Sitter symmetry, the past boundary need not be a place of infinite curvature. Space-time can be extended in a mathematically regular way, and geodesics that seem to end can be given a longer history in a broader setting. But when realistic fluctuations are included, the same analysis suggests that the conditions required for such an extension become much harder to satisfy. If the density variations near the would-be boundary are more than extremely small, they can turn the would-be gentle horizon into a genuine singular surface where curvature scalars blow up. This raises a subtle point about the interplay between structure formation and the possibility of a universe without a true beginning. The very ripples that are needed to build complexity in the late universe may work against the existence of a smooth extension in the early universe. If the fluctuations are too large near the earliest approachable times, they act as seeds not only for galaxies but also for strong curvature regions that prevent the continuation of geodesics. If, on the contrary, the fluctuations are extremely suppressed near the boundary, so that space-time is almost perfectly smooth there, an extension may be possible, but then a mechanism must be found to generate the observed spectrum of fluctuations at later times. In either case, the link between small primordial ripples and the global question of a beginning becomes tight. From an observational angle, measurements already constrain the amplitude and statistics of the fluctuations back to very early epochs. The pattern of hot and cold spots in the cosmic microwave background encodes information about the density field when the universe is only a few 100,000 years old. The smoothness of that pattern, combined with detailed features such as acoustic peaks, points to a specific range of fluctuation strengths and to correlations that are consistent with simple inflationary origin. By itself, this does not prove anything about whether there was a true beginning, but it does mean that any model that changes the deep past must be compatible with the ripples that are actually seen in the sky. From a theoretical angle, the study of fluctuations forces cosmologists to confront the limits of the background plus perturbations picture. Near a would-be bounce or near a boundary that might be extendable, it is not always valid to assume that deviations from homogeneity remain small. In regimes where quantum gravity becomes important, the very distinction between background and fluctuation may lose its meaning. The space-time metric might not be a fixed classical object with small quantum ripples, but a quantity that itself emerges from underlying degrees of freedom with their own fluctuations. In such a setting, the classical language of geodesics threading through a smooth or slightly perturbed geometry becomes an approximation with a limited range. Yet even with these caveats, the lesson from tiny ripples is clear. The existence of small but real density fluctuations is not a detail that can be switched off while discussing the deepest questions. It is a central fact of the universe tied to both its visible structure and to the mathematical behavior of its earliest phases. Any attempt to imagine a cosmos that did not start with a sharp Big Bang must account for how these fluctuations behave near the earliest accessible boundary and for how they connect to whatever, if anything, lies beyond. Classical general relativity treats space-time as a smooth fabric that can be bent and curved by matter and energy. This description works extraordinarily well across a vast range of scales, from the interior of the solar system to the large-scale expansion of the universe. Yet as the history of the cosmos is pushed further back toward high densities and extreme curvatures, the assumptions behind this smooth picture become strained. At some point, quantum effects, which are crucial for understanding atoms and fields at small scales, must also influence the geometry of space-time itself. The region near a putative Big Bang, where curvature would be enormous in the classical model, lies squarely in this regime. In that domain, a complete account cannot ignore quantum gravity, the still unfinished theory that should merge the rules of quantum physics with the geometry of space-time. Quantum theory describes matter and fields in terms of probabilities and fluctuations. Energies and positions do not have definite values until they are measured, and fields exhibit zero-point motion even in their lowest energy states. In most circumstances, space-time is treated as a fixed background on which these quantum processes occur. Gravitational effects are then weak corrections. Near a classical singularity, however, the energy densities predicted by general relativity grow so large that the quantum behavior of matter can no longer be considered a small effect. Moreover, the gravitational field itself encoded in the metric may need to be treated as a quantum object. In that situation, the idea of a definite space-time geometry that bends smoothly down to a point of infinite curvature is no longer trustworthy. Instead, the geometry may fluctuate, superpose, or take on discrete structures at the smallest scales. Various approaches to quantum gravity attempt to describe this regime. Some, inspired by the quantization of ordinary fields, treat the metric as another field to be quantized on a background and then seek corrections to the classical equations. Others, such as loop-based frameworks, suggest that space-time has an underlying discrete structure with areas and volumes built from fundamental quanta. String-based pictures propose that the basic entities are extended objects rather than point particles, and that space-time emerges from their consistent interactions. Although these approaches differ in detail, they share a common message. Near regions where classical curvature would diverge, the new quantum rules can soften or modify the behavior of space-time. Instead of a sharp singularity, there may be a phase where notions like distance and time lose their usual meaning. In some loop-inspired cosmological models, for example, the discreteness of geometry at small scales leads to an effective repulsive force at extremely high densities. In simple versions of these models, a contracting universe that would classically have collapsed into a singularity instead undergoes a bounce at a finite but very high density. The scale factor reaches a non-zero minimum and then increases again. In that picture, the hot, dense state that resembles the early universe is not the first moment of time but the aftermath of an earlier contracting phase. The singular classical Big Bang is replaced by a quantum bridge that connects two semi-classical regimes. The details of this bridge depend on the specific implementation, and it is not yet clear whether such a mechanism survives in more complete versions of the theory. But it illustrates how quantum gravity can in principle remove a beginning of classical spacetime without erasing the existence of a hot early epoch. String-inspired scenarios offer different possibilities. In some, the universe exists in a quasi-static configuration at very high density and temperature for an extended period with strings and branes in thermal equilibrium. A later transition leads to expansion and cooling, giving rise to a phase that resembles the standard Big Bang evolution. In others, collisions between higher dimensional surfaces generate bursts of energy that play the role of a Big Bang within a larger structure. In yet another line of thought, space-time itself emerges from more abstract entities such as entangled quantum degrees of freedom or algebraic structures. In that case, the question of a beginning shifts from the start of space-time to the origin of those deeper ingredients, which may not be organized by time in the usual way at all. From the perspective of geodesic incompleteness and curvature, blow-up quantum gravity can act in two broad ways. It can prevent classical curvature from ever reaching infinite values by altering the equations near the would-be singularity, or it can indicate that the language of geodesics and curvature loses its meaning beyond a certain threshold because the concept of a smooth manifold breaks down. In the first case, the classical singularity is resolved into a regular, perhaps highly curved region that can be passed through. Geodesics suitably generalized to the quantum regime may extend beyond the classical boundary. In the second case, the singularity is replaced not by another smooth region, but by a different kind of description altogether, in which questions about extension and completeness must be rephrased. The observational consequences of these possibilities are subtle. Quantum gravity effects are expected to be strong only at densities and curvatures far beyond what can be reproduced in experiments on Earth. Any imprint they leave on the cosmic microwave background or on the distribution of galaxies is likely to be small and indirect. Some models predict small deviations from the simplest inflationary predictions, such as slight changes in the spectrum of primordial fluctuations or the presence of particular patterns in polarization. Others suggest that relic gravitational waves from a pre-Big Bang or bouncing phase could persist carrying information about the earliest times. Detecting such signatures is challenging. It requires extremely sensitive measurements and careful separation of signals from foreground noise. Even without decisive observations, quantum gravity reshapes the conceptual landscape. In a universe that is governed solely by classical general relativity and ordinary matter, a singular Big Bang appears as a robust feature under broad conditions. When quantum effects are included, that robustness weakens. The region that once looked like an unavoidable beginning may be replaced by a quantum domain with different rules, a domain that either connects to an earlier phase of space-time or stands as an origin of classical time without being a singular point in the quantum sense. The precise nature of that domain remains unknown. Different candidate theories propose different structures, and none has yet achieved the kind of empirical support that would elevate it from speculation to established science. At the same time, quantum gravity does not automatically guarantee a universe without a beginning. Some formulations allow for histories in which space-time still has a finite past, even though singularities are softened or removed. In such cases, the Big Bang is transformed rather than erased. It becomes a quantum event or transition beyond whose description lies a region where the parameters of the theory may not extend in a simple temporal way. The question then is not only whether the universe started, but what it means for a quantum spacetime to have a start when time itself is part of the structure being described. In this way, the search for a theory of quantum gravity deepens the mystery around the origin of the universe. It shows that the classical picture of a singular Big Bang is incomplete, but it does not yet replace that picture with a single clear alternative. Instead, it opens a range of possibilities in which the hot, dense early universe is embedded in a more complicated quantum story. Some versions point to a prehistory, others to a timeless underlying layer from which time emerges. All suggest that the question of whether the universe began with the Big Bang cannot be answered fully until the quantum nature of space-time is understood. Even within the uncertain territory of quantum gravity, a broad theme appears. Many speculative pictures of the cosmos try to avoid a single isolated beginning by placing the familiar Big Bang into a larger pattern. Sometimes that pattern is temporal, with the universe passing through cycles of expansion and contraction, or through repeated episodes of reheating. In other cases, the pattern is more abstract, with time itself emerging from a deeper level of description that does not possess an ordinary notion of before and after. In both kinds of ideas, the hot early universe is still present, but it is not the absolute first event. It is a feature of a larger story, whose structure can be very different from the simple linear timeline suggested by classical cosmology. Cyclic models start from the observation that general relativity does not forbid a universe that expands and contracts repeatedly. In such a scenario, a phase of expansion like the one seen today eventually slows and reverses. Distances between large-scale structures begin to shrink, densities rise, and temperatures climb. In classical terms, this contraction could lead to a singular state. In a cyclic picture, however, new physics at high density intervenes. Instead of ending in a singularity, the universe undergoes a bounce and enters a new expanding phase. Each round of contraction and bounce is followed by a new Big Bang-like episode with hot matter and radiation filling space, and then cooling as expansion proceeds. The cosmic microwave background observed today would then record conditions in the current cycle, while previous cycles lie beyond direct view. These cyclic constructions must address a basic thermodynamic challenge. In an ordinary process, entropy, a measure of disorder, tends to increase. If cycles simply repeated without any mechanism to reset or dilute entropy, later cycles would inherit the accumulated disorder of earlier ones. Over an extremely long history, structures would break down, and the cycles would no longer resemble each other. To maintain a universe that remains regular enough for galaxies and stars to keep forming cyclic models often rely on phases of very rapid expansion, or on mechanisms that remove or dilute entropy between cycles. Some versions incorporate an inflation-like stage into every round, with expansion smoothing and stretching irregularities after each bounce. Others appeal to the behavior of extra dimensions or to exotic fields that play a role only near the transition. From the viewpoint of an observer living in any one cycle, the hot early phase would still appear as a beginning. The observable universe would have a finite age since its last bounce. The cosmic microwave background would still look like the afterglow of a hot, dense state. Geodesics traced backwards would reach a boundary at the bounce. What changes is the global picture. Instead of a single origin, there is a chain of phases extending further into the past. Whether that chain itself has a first link or whether it continues without limit depends on the details of the model. Some cyclic proposals explicitly assume an infinite sequence, while others allow for a finite but extended prehistory. Another class of ideas, still speculative, treats the remote future of an ever-expanding universe and the very early stages of a new universe as related in subtle ways. In such pictures, the universe expands for unimaginably long times matter, decays, black holes evaporate, and only very dilute radiation remains. At such late times, scales of time and distance lose much of their practical meaning. Under certain mathematical transformations, this very distant future can be mapped to a new early phase with high effective density. A new cycle begins not through a literal bounce of a collapsing universe, but through a re-identification of the far future of one phase with the Big Bang of the next. The Big Bang becomes a junction between aeons rather than an absolute start, and the arrow of time in each aeon points away from its own Big Bang, even as the chain of aeons has no single first member. There are also proposals in which time does not exist as a fundamental quantity at all. In these emergent time pictures, the basic ingredients of reality are described in terms of quantum states and their correlations without assigning them to specific moments in a pre-existing temporal order. Time appears only in an approximate way when large numbers of these degrees of freedom are organized into patterns that can be parameterized by a variable that behaves like time. In such a framework, the Big Bang is not the first instant of a timeless background, but the point at which a particular coarse-grained description becomes valid. Before that point, questions that rely on ordinary notions of before and after may not have clear answers because the variables needed to pose them have not yet emerged. In emergent scenarios, the early universe can be seen as a phase transition in the underlying quantum system. As certain correlations build up an effective space-time geometry becomes a good description. The scale factor curvature and geodesics used in classical cosmology then appear as tools that summarize the behavior of many microscopic degrees of freedom. The hot, dense state associated with the Big Bang marks the onset of this emergent geometry. Asking what happened before that state translates into asking about the properties of the deeper system in a regime where the notion of time is very different. An underlying timeless rule may govern the ensemble of possible configurations, while time as experienced in cosmology is tied to the path that the system takes through a subset of those configurations when certain approximations hold. Cyclic and emergent views share a common effect on the idea of a beginning. They weaken the connection between the hot early universe and the absolute start of everything. In a cyclic universe, the Big Bang is one event among many in a repeating pattern. In an emergent universe, it is a threshold where a particular description becomes meaningful. Neither type of model necessarily avoids all forms of boundary. Cycles may still require an initial choice of conditions at some stage. Emergent time may still arise from a structure that has its own form of origin. But the simple image of a single explosive moment that brings both space and time into existence is replaced by a more layered picture in which that moment is embedded in a larger context. From an observational standpoint, cyclic and emergent ideas are difficult to test. Some cyclic models predict that traces of previous cycles could leave subtle marks in the cosmic microwave background, for example as faint anomalies in the distribution of temperature fluctuations on large angular scales, or as specific patterns in gravitational waves. In practice, the data are noisy, and many effects can mimic one another. Emergent models might imply slight deviations from the simplest inflationary predictions or new relationships between entanglement and geometry, but these are not yet tied to clear unique signatures. As a result, the status of such models remains provisional. They offer logically coherent ways to think about a universe without a unique beginning, but they have not yet gained the firm empirical support that anchors the standard Big Bang framework. On the conceptual side, these scenarios broaden the range of possibilities for how the cosmos might be organized. They show that a universe can have a hot early phase without that phase being the first thing that ever happened. They also introduce new questions such as how entropy behaves across cycles, how emergent time arises from more primitive structures, and how the arrow of time is set. Rather than giving a simple alternative to a Big Bang origin, they shift the puzzle to deeper levels. The universe may not have started with the Big Bang in the classical sense, yet the conditions that allow cycles or emergence themselves call for explanation. In this way, attempts to remove the Big Bang as a beginning do not eliminate the mystery of origin. They reframe it in terms of patterns over many cycles, or in terms of the rules that generate space-time itself. The present universe carries quiet records of its past in every direction on the sky. The expansion seen in the recession of galaxies, the faint microwave glow that fills space, and the web-like distribution of clusters and voids all act as observables that guide cosmological models. The standard Big Bang framework with a hot early phase followed by cooling provides a coherent explanation for many of these clues. It links the uniform spectrum of the cosmic microwave background to an early state close to thermal equilibrium. It relates the abundance of light elements to nuclear reactions in a dense young plasma. It describes how small initial fluctuations grow through gravity into the structures observed today. Any alternative picture in which the universe did not truly begin with a Big Bang must still account for the same data with at least the same precision. The cosmic microwave background is one of the most powerful constraints. Its spectrum is extremely close to that of an ideal blackbody, indicating that the early universe was once in a nearly uniform hot and opaque state. The tiny variations in its temperature across the sky encode the pattern of density fluctuations at the time when matter and radiation decoupled. The positions and heights of the acoustic peaks in its power spectrum reveal how sound waves propagated in the primordial plasma, and they depend sensitively on the expansion rate, the composition of the universe, and the geometry of space. Any model with a bounce and emergent phase or an embedding in a larger space-time must reproduce these features. It must deliver a hot, dense phase with the right properties, even if that phase is not the absolute beginning. On larger scales, surveys of galaxies map out a three-dimensional picture of the cosmic web. Filaments, walls, and voids form a pattern that matches the evolution of initially small fluctuations under the influence of dark matter and dark energy in an expanding background. The scale of certain preferred features, such as the baryon acoustic oscillation signature, provides a standard ruler that traces how distances grow with time. Weak gravitational lensing, in which the shapes of distant galaxies are subtly distorted by intervening mass, adds further information about how matter clusters. Together, these observations test how the universe expands and how structure forms over billions of years. They favour a history in which the universe has been expanding for a long but finite time from a hotter, denser state. They do not by themselves tell whether that state was a true beginning or a transition from something earlier. Future observations aim to reach further back and to probe more subtle effects. Measurements of the polarization of the cosmic microwave background can search for the imprint of primordial gravitational waves, which would carry information from very early times and from high-energy processes such as inflation or pre-Big Bang phases. Attempts to detect a background of gravitational waves through observatories on Earth and in space, and through timing of pulsars, may reveal signals from processes that occurred before the universe became transparent to light. Observations of the faint emission from neutral hydrogen in the early universe through the 21 centimeter line promise to map the so-called dark ages before the first stars formed. Each new window adds layers of detail to the story of how the hot early universe evolved, and each constrains the space of allowed histories. Despite this growing wealth of data, there are limits that cannot be crossed. The observable universe is bounded by a horizon. Light has had only a finite time to travel since the hot phase, and regions beyond a certain distance cannot yet have sent signals that arrive today. Even within the horizon, the finite number of observable modes means that there is a fundamental level of cosmic variance, a limit to how precisely certain properties can be measured. No observation can see directly into the regime where quantum gravity is dominant. The earliest moments of the hot phase and any prior episodes are separated from present instruments by both physical opacity and theoretical uncertainty. As a result, many distinct models can be tuned to reproduce the same set of observables over the times and scales that are accessible. This degeneracy appears clearly when alternative histories are examined. A bouncing model that passes through a high-density phase then inflates can generate fluctuations that look almost identical to those produced by an inflationary model with a singular start. An emergent model in which the universe lingers in a quasi-static state before beginning to expand can with suitable choices of parameters deliver a hot early phase whose observable imprint is nearly indistinguishable from that of a conventional Big Bang with inflation. Even an embedding in a larger de Sitter like spacetime can leave the local observables unchanged, as long as the physics within the observable patch follows the same rules. In each case, the same data that support the standard picture also admit more complicated stories that differ mainly in regimes that lie beyond direct reach. For cosmologists, this situation creates both a challenge and a direction of work. On one hand, the success of the standard framework in explaining the cosmic microwave background, nucleosynthesis and large-scale structure, makes it a robust, effective description of what is seen. On the other hand, the inability of current observations to distinguish cleanly between a universe that truly began in a classical singular Big Bang and one that entered a hot phase after a bounce or a quantum transition keeps the question of origin open. Efforts focus on finding observables that might break this degeneracy. These include specific signatures in the spectrum of primordial fluctuations, small departures from scale invariance at particular wavelengths, traces of non-Gaussian statistics or characteristic patterns in the gravitational wave background that would point to a particular prior phase. So far, no single measurement has provided a definitive indication that the universe passed through a stage before the hot phase described by the Big Bang model. At the conceptual level, the data pose an intriguing possibility. It may be that for all practical purposes, the universe will always look as though it began with a Big Bang, even if the deeper reality is more extended. The combination of limited observational reach and the smoothing effects of processes like inflation can erase or hide direct traces of earlier epochs. If a bounce erased most memories of the contracting phase, if emergent time left no clear marker of its own onset, or if a larger embedding spacetime interacts only weakly with the observable patch, then no experiment carried out within the horizon could conclusively reveal that history. The hot dense state would then function as an effective beginning. It would be the earliest moment to which observations can be tied regardless of what lies beyond in theory. At the same time, the universe continues to provide new data. Each more precise map of the cosmic microwave background, each deeper galaxy survey and each new detection of gravitational waves refines the constraints on cosmological models. Some speculative scenarios are already limited or disfavored because they would have produced patterns that are not seen. Others remain compatible but untested at crucial scales. The process of comparing theory with observation is gradual. It may eventually narrow the range of viable histories to a small subset, or it may leave several broad possibilities that differ mainly in regions forever hidden behind horizons or quantum domains. In this way, the question of whether the universe started with the Big Bang remains tied to both theory and measurement. The sky records a history that begins as far as current evidence can see, in a hot dense state, and evolves into the expanding cosmos of galaxies and background light observed today. Whether that recorded history is the whole story, or only a chapter in a longer or more abstract narrative, is not yet decided. The data strongly support a Big Bang in the sense of a hot early phase, but they do not yet resolve whether that phase is the first page of space-time or a later scene in a deeper cosmic play whose opening acts may never be fully reconstructed.